we learned what parametric equations are. So if I have on the plan and I have a curve where its x-y coordinates are being described by a parameter. Okay, so this is, for example, this is from t is in the interval 0 to 1. This is an example, okay? In general, you can say t is in the interval a, b. Okay, the starting time is a, the stop time is b. Okay, so then you will have when t equals 0, the xy is here. When t equals, let's say, 0.1, the xy is here. And when t equals 1, the xy is here. So that's a example of parametric functions. Then I can say, so parametric equations. Then I can say, how about let me define a function using parametric functions. Then let's call it vector valued function. Okay, so let me remove this and give you a concrete example. So let's say I have a vector, but this vector is now a function, meaning at different input t, you have a different output vector r of t. And what is my output vector depends on the parametric equations that you get. Let me use an example, cosine of t and sine of t. Okay, so in this case, I have the x of t being defined as cosine of t and the y of t being sine of t. Okay, this is what we're given. Suppose we're given a vector valued function like this, then by the parametric equation, then what do we see? Okay, so let me draw the graph for you. R of 0, that is the vector cosine 0 and sine 0, which equals 1, 0. So if I'm just treating this as a vector, then 1, 0 is this vector, right? And R of pi over 4 is cosine pi over 4, sine pi over 4, and that is 1 over root 2, 1 over root 2. It's the vector of length 1 at angle pi over 4. Okay, so this seems to be too long, pi over 4. Why do we know that? Because I happen to know this gives me the coordinates on the unit circle. Okay, if you don't remember the coordinates on unit circle, you can go back. You can go watch the supplemental videos I made for trig functions, sine and cosine. Okay, so this vector is my r of pi over 4, but it doesn't just jump from here to here. It moves according to t. So t equal to 0 here, t equal to a little bit larger of 0, that's here. So if you think this is an animation, the tip of the arrows, it travels like that. Okay, and pi over 2 gives you this vector 0, 1. Okay, so it keeps going like that and then goes like this. Okay, so you can see that the vector value function, if I look at the trace of the tips, it gives me the curve that's given by this parametric equations. Okay, so this is like we're looking at two sides of one coin. Okay, so we can talk about a curve using parametric function equations. We can talk about curve using vector valued function, and the coordinates in the vector are given by the parametric equations. Okay, and because it's in R2, so I know it gives me a curve that's in a plane. If I have a vector valued function in R3, this time I have 3 components, then traveling along the tip of the vectors, I could get something like this, right? It doesn't have to come back, it can just be a piece of string like that. Okay, just arbitrary. Then you can see this gives me what, a curve in R3. So sometimes we also say this as a space curve. Okay, so far you have learned a few terminologies. You learned what in general parametric equations are, and you learned that you can use the parametric equations to write a vector valued function. Vector valued means the output value, vector values means the output value is a vector. Okay. And this in result will give you a plane or space curve. Okay, so we will interchangeably using these terms, vector valued function.